This first video here is going to be a sort of a general overview of three major perspectives on what makes science work. The videos from here on out are primarily derived from a course I teach at my university, and I wanted to let you all know what the textbook I used for that class is. It's called Theory and Reality. It's by Godfrey-Smith, and it's a book that I highly recommend. Now, there's many controversies surrounding science and within various scientific disciplines, but no matter who you are, no matter what perspective you take on any of these disciplines, one thing is obvious: science works. This was very captured rather brilliantly by this fantastic XKCD comic, which I believe is now sort of, immortal, in particular amongst scientists. So we can start from that admission, but then we have to ask a question: exactly how does it work? What is it that makes science so successful, so useful, so powerful? It's all too often for people to simply reduce science to empiricism, and obviously there's something to this. Science, according to this view, is a focused, organized, and systematic version of what we all do every day. We experience the world and we gain knowledge about it. Science just takes that very sort of common sense approach and expands on it. But of course, it's frankly kind of naive to think that this is all that there is to science. When we look at science in the flesh, as it were, we're going to see that it's much more complicated. So probably the best way to see this is to take another quick look back at some events in the history of science. So I want to give one example here that comes from Carl Hempel, an important 20th century philosopher of science. And it's the example of Ignaz Semmelweis, which some of you probably know, because Semmelweis was one of the people who really sort of started pushing the germ theory of disease. He through all sorts of very, very rigid scientific empirical experiments, he was able to prove that doctors that washed their hands before they delivered babies greatly reduced postpartum infections, both in the mothers and in the babies. His data, when looking at it in retrospect, seems fairly undeniable. So a straightforward sort of empiricist picture of science would think that Semmelweis would get recognized, he would get promoted, but that's actually not what happened at all. Semmelweis was fired. He was causing trouble, and the scientific establishment viewed him as someone who was simply, a troublemaker. So instead of getting promoted and getting credit and getting scientific recognition, he was disgraced and he was kicked out. So scientific practice did not work the way scientific theory, and then by here I mean, of course, again, the theory that empiricism puts forward about science, says it should. So why exactly is that? What went wrong with this sort of idealized vision we have of science as being purely guided by data and evidence? In this instance, the scientific practice didn't match up with the way that we thought science was supposed to work. Now, you might be tempted to just write this off as being anomalies, but actually you'll find out that when you take a look at the history of science, this happens very, very frequently. In fact, later on when we get to talking about Thomas Kuhn's going to say that this is an essential element of science. Without this sort of thing, we could not have science. So don't be so quick to just write it off. Now, if we move forward in time just a little bit, we come to a specific instance where this sort of empiricist view is again challenged. There was a cholera outbreak in London, and it was mapped to a very specific water pump. They found that when you radiated outward from this water pump, the rates of infection went down, and the closer you got to the water pump, the more they went up. One of the people who put this forward was the French chemist Louis Pasteur. Now, Pasteur, of course, was pretty important in the time. He was a very big name, and he argued for the germ theory. He had a competitor, though, by the name of Max Pettenkofer, and Pettenkofer wanted to reject the germ theory of disease, and so he performed, again, a fairly straightforward empirical experiment to prove the germ theory was wrong. In front of a large public audience, Pettenkofer deliberately drank a glass from that infected water pump, and it was full of these, supposed cholera germs. Pettenkofer never got sick. The idea was that, if Pasteur was right, if we got sick from germs, then Pettenkofer should have gotten sick. He didn't get sick. Doesn't this falsify Pasteur's germ theory of disease? Now, of course, we know today that it doesn't. We know today that Pettenkofer was not only wrong, he was also ridiculously lucky. Cholera is, in fact, caused by germs. But this creates a bit of a problem. How are we to understand this relationship between empirical evidence and scientific theory? How does evidence prove a theory? How does it disprove a theory? This is a complicated issue, and you'll find that you can't really solve this issue simply by looking at empirical evidence itself. You have to go beyond empirical evidence in order to sort out this question about empirical evidence. To foreshadow a little bit something we're going to talk about later on, this sort of, again, this simplistic empiricist picture, it can't work, not only for these reasons that I've suggested, but it actually has some fairly deep roots, the flaw has some fairly deep roots in human psychology. The human psyche does not work the way naive empiricism suggests it should. The human mind is not, to use the phrase from John Locke, simply a blank slate, or, to use a different metaphor, a dry sponge that just absorbs information from around it. The human mind actually participates in many ways in the construction of its understanding of the world. And that means that this sort of simple empiricist picture where we just take in information isn't going to work quite that straightforward. Like I say, we'll come back to that. But for now, I want to take a look at something that Galileo says to suggest our second approach to science. Galileo claims that nature is written in the language of numbers. And what makes science so powerful, what makes science works, is that it translates that language, which again, in the native tongue we can't really understand, into something that we can grasp, into something that human beings can understand. So we can, quite literally, converse with nature. So this is what distinguishes science from other endeavors, according to Galileo's view. It's the fact that it employs mathematical models of nature. And when you combine these mathematical models, again, with the information that you get from empiricism, you get a sort of more robust, more sophisticated view of science. Now, again, you might be tempted to just think, well, of course, both of these views are right. We'll just, take both. We'll have our cake and eat it too. We'll have empiricism and we'll have mathematics. And obviously there's something to that. But like I said before, there's going to be a bit of a complication here. It's not going to be as simple as just taking both. So this points to actually an age-old problem in philosophy, a problem that long predates modern science, and it's the tension between reason and experience. For much of the history of philosophy, and for that matter, the history of science, reason and experience were seen as competitors. One or the other was taken to be the true foundation of knowledge, knowledge here with a capital K. Either it was reason or it was experience. Ultimately, true knowledge had to boil down to one or the other. And there's been a long list of people in this debate. It predates Socrates. It goes back to the pre-Socratic philosopher Parmenides, who argued on the side of reason, and then later on Plato and sort of Socrates by extension. Galileo, who we've just been talking about a little bit, and more in modern philosophy, René Descartes. These four figures were all champions of the idea that reason was to be found at the foundation of true knowledge. Experience, in as much as it gave us any knowledge, was sort of an inferior form of knowledge, not a real legitimate form of knowledge. On the other side of the debate, you have experience. The pre-Socratic philosopher Heraclitus is important here. Actually, I'm sorry, that picture there's of Aristotle. There we go. There's Heraclitus right there. Heraclitus, who was a near contemporary of Parmenides, they sort of got this debate started. Aristotle, of course, was Plato's student. They continued this debate. And then Francis Bacon, who I talked about in the history of philosophy. These three figures were champions of experience. And these lists could be extended, of course. But this is one of the more protracted debates in the history of epistemology, which is the branch of philosophy that deals with the nature and extent of human knowledge. Now, while this was a huge debate for a long time, in recent years, recent decades, it's kind of calmed down somewhat. There isn't really this sort of strident rationalist empiricist divide anymore. Most philosophers, most epistemologists seem to agree that rather than simply picking one or the other, some sort of combination account is going to be the way to go. The only real question is precisely how that combination is going to work out. So math obviously is an important part of science. You can't really do science professionally nowadays unless you have a very strong grasp of math. But at the same time, math can't claim all of the success of science. Many of the most important scientific breakthroughs in the history of science required virtually no math at all. And probably the best example here is the work of Charles Darwin. And the work that Darwin did had very little in the way of mathematical modeling. After the neo-Darwinian synthesis, and you get genetics in there, and then of course population population genetics and that sort of thing, math and mathematical modeling does eventually come into evolutionary theory. But Darwin's work, the work that Darwin himself did, had very little, if any, math at all. So math, again, while a big part, can't really take credit for all the success of science. So I want to look now again, our third and final vision of science, and this one is probably best recalled if you remember Newton's famous quote, "If I have seen far, it is because I have stood on the shoulders of giants." It's a very famous quote. Most of you probably heard it before, and this points us in another direction for science. The idea that what makes science work is its very unique social structure. Science is not something that happens in a vacuum. It's not something that individuals do alone. Individuals, again, they may perform math on their own, they may perform sort of rudimentary empirical experiments on their own, but science, according to this view, is something that is of a higher order. It's something that's engaged in on a social level, with many participants working together to create this social construct that we call science. Probably one of the most obvious examples of the social structure of science is the importance of peer review. Talk to any professional scientist, and they'll tell you how important peer review is for making sure that scientists are kept honest, that there isn't unethical forgery or things like that, that there isn't total kooks get into the literature. Peer review is again a flawed but nonetheless essential part of the scientific process. And you can expand out from that about how the importance of cooperation and trust. No individual scientist can check the results of every other scientist. They have to assume that the social structure of science has done its job. They have to assume that other people have checked this work, and so they can rely on it when doing their own research. And without that cooperation, without that trust, we couldn't build on the work of previous scientists, and that means that we couldn't have anything at all like scientific progress. One of the important steps forward in the scientific revolution was the development of social scientific societies. Probably the most famous example of this is the Royal Society of London, a group that Newton was a part of and that still exists to this day as one of the most important and renowned scientific societies. And these groups came about in order to check and coordinate and police themselves to make sure that everyone was doing science right. And it's this social structure, according to this view, that really distinguishes science. I mean, after all, empiricism and experience can't really distinguish science from other endeavors. Everyone has experiences. Experience isn't something that really distinguishes science from any other sorts of endeavors. Even crazy things that we consider pseudoscience, like astrology and feng shui. There's a sense in which these things derive from experience and rely on experience. So it's not experience per se that really matters here. It's somehow connecting and unifying all of our experiences in a way that allows us to generate, develop, and test scientific hypotheses. That's what really makes science unique and special, according to this view. Now, like I said, obviously all three of these elements, empiricism, math, and the social structure of science, play important roles in how science works. These aren't competing visions. It's not like you have to choose one or the other. All three of them are important elements in science as a whole. But at the same time, because science is pluralistic in this way, because it relies on all three of these elements and more, of course, things can get very, very complicated. What happens, for example, when these three elements seem to pull in other ways? What happens when the social structure, the social inertia of science goes against empirical evidence? What happens when you have an experiment that appears to contradict the socially accepted dominant paradigm? That's not entirely clear as to how we should parse that out. What do you do when the mathematics seems to not match with our empirical experiences? This sort of thing happens an awful lot in quantum mechanics. This creates philosophical and scientific problems which are not easy to parse out. And in some ways, many of the problems, certainly not all, but many of the problems that we're going to see in future videos in this series can be seen as difficulties in trying to harmonize these three elements of science with each other. Now I want to sort of rewind to the very beginning of the history of the 20th century in the philosophy of science and take a look at what was the most important school of philosophy of science in the early part of the 20th century, a school of thought known as logical positivism. And we'll look at both the rise and the fall of logical positivism next.